In section 3 of the prerequisite chapter, we're going to look at radicals and rational exponents. So this is again a review of skills that you should have already acquired from Algebra 1 and Algebra 2. So if we look at the first example here, it has a raised to the m divided by n. So what you want to remember here is that the numerator, when you have a radical exponent, the numerator is your exponent and the denominator is your root. So I can rewrite this as the nth root of a to the m, or I can do it as the nth root of a to the m. If we look at example B, here you have the nth root of a followed by the mth root of a. You can multiply these two roots to get the mnth root of a. If we look at the next one where we're taking roots, the same root, so this is the nth root in both cases, but what we're taking the root of differs, but we're multiplying those roots, we can multiply what we're taking the roots of. If we look at the next example, if we're taking the nth root and then the nth power, that's going to turn into just, they kind of cancel each other out if you think about it. If you take, let's say, the square root of 16 and then square it, you're going to take the square root of 16 as 4, and when you square it, you get 16 back. So squaring and square root would undo each other. If we look in example E, we're taking the nth root of two different things, but we're dividing. We can divide those expressions first before we take the root, if that makes it easier. And then in the last example, in example F, we're taking a to the n and then the nth root of that. And if n is even, if we're taking an even root, then it's the absolute value of a. And if n is odd, we're taking the odd root, then it's just whatever a is. The reason they are stating that is because we can't take an even root of a negative number. So this value, this a value, when we're doing evens, has to be positive. That's why they're saying that it has to be the absolute value of a. It has to be positive. Whereas we can take an odd root of a negative number. You can take the third root, for example, of, let's say, negative 27. So the third root of negative 27 is negative 3, okay? Whereas we cannot take, like, the fourth root of negative 16, because you can't take an even root of a negative number. So that's the difference there between the absolute value of a and just a. So let's look at some examples. So in this first one, we're taking the fourth root of 16 squared. So if you don't know 16 squared off the top of your head, there's a couple different ways you can do this problem. You could do 16 squared and get 256, and then take the fourth root of 256 and get 4. But our goal with these radicals and being able to simplify them is to be able to do it in our head without a calculator. And if you weren't overly familiar with perfect squares, you may not have known in your head that 16 squared was 256, and so that would have made it harder for you to try to do in your head, and especially to take the fourth root of that and know it was 4. So here's the alternative way to do it. I'm going to rewrite 16 as 4 squared raised to the second power. And if we use our exponent rules we learned in the last set of roots, we're going to multiply those and get 4 to the fourth. So the fourth root of 4 to the fourth is just going to be 4. The absolute value of 4, which is still 4. Because remember, with even roots, that's going to be the absolute value. Now, if we look at this next example, we can't take the third root of 9 evenly, and we can't take the third root of 3. But since they're both the third roots, we can multiply what's under the radicand and get third root of 27, and we can take the third root of 27. That is in fact 3. Again, with letter C, the fifth root of 32 and the fifth root of 8 is not really obvious to us. So we're going to take the fifth root of 32 eighths, and I can simplify that to the fifth root of 4, and I can't simplify that any further because there's not a whole number answer to the fifth root of 4. If we look at this next example, they're looking for the square root of 256 and then the fourth root of that. So one option to do this problem would be you could take the eighth root of 256. Now, I don't know that off the top of my head. So I'm going to go back and work it the other way. I'm going to take the square root of 256, which is 16. And I know that from example A that we worked through. And then I'm going to take the fourth root of 16, which is 2. Those are a little bit smaller numbers to be able to work with. Now notice in letter E, we have the fifth root of 25 raised to the fifth. Those are going to undo each other and leave us with 25. And if we look at letter F, you really have two options here. You can either take 27 to the fourth and then take the third root of it, or you can take the third root of 27 and raise it to the fourth. Now, I'm going to go with the second option because in the first option, I don't know what 27 to the fourth is off the top of my head, nor could I then take the third root of that. That's just too big a numbers for me. Yeah, sure, you could plug it in a calculator, but our goal here is to do it without a calculator. So if I take the third root of 27, I get 3, and then I'm going to raise that to the fourth power. So 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So those were kind of examples of each of the properties of radicals and how we would work through them. Notice that sometimes I didn't use the property. For example, in letter D, it was harder to use the property and try to find the eighth root of 256 than to not use the property and just work myself through the order of operations. So you have to make wise decisions on these. Now, the simplest form of a radical expression has to have 3 things. There are no fractions under the radical, no radicals in the denominator. We often refer to this as rationalizing the denominator. And all perfect squares, cubes, whatever root you're taking, factors are taken out of the radical. What does that mean? Well, here I'll give you an example. For example, let's say we have the square root of 18. Now, the square root of 18 is not a perfect square itself, but there's a perfect square factor in there of 9. So you've learned to change that into the square root of 9 times the square root of 2, and then we take the square root of 9 and change it to 3 root 2. So that then would be the simplest form of the radical expression. Let's look at some examples. So when they ask us to simplify, we want to make sure we've done all those things. So in the first one, I'm going to look at first the square root of 72. Now the square root of 72 is not a perfect square. But again, there's perfect square that is a factor of 72. And that would be 36 times 2. So I split that up as root 36, root 2. And then x to the 5th, root x to the 5th. So the square root of 36 is 6. and I can't simplify root 2. Now we need to figure out what to do with our x to the 5th. So if we again think of creating perfect square factors, x squared would be a perfect square. I could take, I'm going to move this up here, x to the 5th and rewrite it as x squared times x squared times x. So if I did that, then this is going to turn into 6 root x squared, root 2 root x. Now my square root of x squareds turn into just x's. So when I simplify that, I get 6x squared. And then I've still got my root 2 and my root x, which I'm just going to put under one root symbol. So let's look at letter B. The 4th root of negative 32 x to the 7th y to the 8th. So first of all, I'm looking for a perfect fourth that might be a factor of 32. So I know perfect fourth is 16. So I'm going to do 4th root of 16, 4th root, negative 2. Because remember, we can't take an even root of a negative number. So I'm going to leave the negative with the 2, which I can't take the 4th root of. Then I'm going to change the x to the 7th into 4th root of x to the 4th and 4th root of x to the 3rd. And I'm going to change the y to the 8th into the 4th root of y to the 4th and the 4th root of y to the 4th. And now if I simplify, I get a 2, I get a 4th root of negative 2, I get an x, I get a 4th root of x cubed, I can't simplify, I get a y and a y. And now if I combine up what's outside my radical, I get 2xy squared, and inside my radical I get the 4th root of negative 2x cubed. I'd like you to pause the video and try this third one on your own. Now, I can take the 3rd root of negative 27. I can take the 3rd root of x to the 3rd, 3rd root of x to the 3rd, 3rd root of x to the 3rd, and I can take the 3rd root of y to the 3rd and the 3rd root of y to the 3rd. Now, as I simplify these, I get negative 3 x, 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 y, y. Which gives me negative 3x cubed y squared. You can also think about it as if you're dividing the exponents under the root by whatever the root is. So this I can really rewrite as x to the 9/3, and this I can rewrite as y to the 6/3. So then I would get x to the 3rd and y squared when I simplify that. Okay, let's look at our next part about radicals. To add and subtract radicals, what has to be true? Well, first you want to simplify each radical. So simplifying each radical means that you have to get that simplest form that we've been working on. Then you can add and subtract terms with like radicals. So let's look at these first ones. When we look at them at first, the radicals are not like in example A, so we can't, it doesn't look like we can add them, but we haven't simplified them first. So since we're doing square roots, I'm looking for perfect square factors of 8. So I'm going to do root 4 times root 2, and perfect square factors of 32, I'm going to do root 16 root 2. Now if I simplify, this root of 4 turns into 2, so I get 5 times 2, which is 10 root 2. And over here, my root 16 turns into 4, so I get 2 times 4, which is 8 root 2. I add those together, I get 18 root 2. Your root 2 is like a variable, so any other terms that have just the root 2 in it, you're going to add those coefficients, the 10 plus the 8, and keep your variable, which is root 2 in this case. Now let's look at our next example. Again, we're looking for, this time, perfect cubes. So I'm going to do the third root of 8 times the third root of 3 to break up 24. And the third root of 64, 64 is a perfect cube. It's 4 cubed. So we simplify that. Now if I change this, I get 2 times the third root of 3 plus 4. And I can't simplify that any further because both terms don't have a third root of 3 on them. So that's the best I can do. Now we're going to skip these challenge examples. We're going to do them in class one day. So I'm going to move on to the rationalize the denominator. Now I mentioned this in the rules that you have to rationalize the denominator whenever you have a radical in the denominator. So we're going to look at letter A first. Letter A is easiest case scenario. You have a single radical in the denominator and it's only one term. We're going to simply multiply by that radical over itself. So I'm going to get negative 15 root 5, and when I multiply the denominator I get root 25. And I can simplify that. You should create a perfect square. So root 25 turns into 5, and then you should be able to simplify here a little bit with your constants, and I get negative 3 root 5 for my answer. Notice no longer a radical in the denominator. Now I'm going to skip next to letters C and D. So in letter C, notice that now our denominator has 2 terms. When there's 2 terms in the denominator, you have to multiply by what's called the conjugate. So the conjugate of an expression is the same expression with the opposite arithmetic. So in this case it's subtraction. We're going to change the arithmetic to addition, but you're going to keep the 2 and the root 5. So I'm going to multiply here by 2 plus root 5 over 2 plus root 5. So I distribute here in the numerator. We get 20 plus 10 root 5. And in the denominator, we're going to have to FOIL. All right, so we do the firsts, which would get us 4. We do the outers, which gets us plus 2 root 5. We do the inners, which gets us minus 2 root 5. And we do the last, which gets us minus root 25. Now, if I simplify this, I'm going to leave my numerator, 20 plus 10 root 5. And in the denominator, notice that this is the beauty of multiplying by the conjugate. The outers and the inners will turn into 0. And then I just have this root 25 is really 5. So I have 4 minus 5, which is negative 1. And then I'm just going to divide each term by negative 1. So negative 20 minus 10 root 5. And that's my final answer. Now, if you think you get the hang of this, try pausing the video and doing D. Otherwise, you can continue on with me. Again, with D, we have 2 terms in the denominator, so we have to multiply by that conjugate value again. So to multiply by the conjugate, I'm going to do root 2 minus root 3. Root 2, you're only changing that arithmetic sign. So this time we're changing from addition to subtraction. So again, I'm going to distribute in the numerator, 6 root 2 minus 6 root 3. And in the denominator, we're going to FOIL. So I get root 4, and I get minus root 6. And here I get plus root 6. And over here I get minus root 9. So again, beauty of multiplying by the conjugate, these outer and inner terms should turn to 0. This turns into 2, and I have a minus 3 over here. So I'm going to get 6 root 2 minus 6 root 3 over negative 1. And we're going to divide through and get negative 6 root 2 plus 6 root 3. Now this does not, I don't want these two examples in the notes to make you think that every time you do this multiplying by the conjugate, you're going to end up with the negative 1 in the denominator. That is not true. Okay? Just so happened in these two cases. Now we're going to go back to B, E, and F. These are more difficult. These I would consider the most difficult ones that we're going to do. And I'm not so sure that you saw these in Algebra 2. If you were in Advanced Algebra 2, you probably did. Regular Algebra 2, I'm not so sure. The thing that throws students off here is they get so used to doing it for the square root that they think it's the exact same thing when you're taking another root. Now, the reason for the square root, like in example A, that we just multiplied by root 5 over itself is because when we take root 5 times root 5, we get root 25, and this is a perfect square. So we can then take the square root of it and get rid of the radical. When we have something like the third root, that means that when we multiply by something over itself, we've got to end up over here with a perfect cube in this case. Okay, so we want to think about what we have to multiply 9 by to end up with a perfect cube. So if we think about the perfect cubes, you've got 1, 8, 27, 64, 125. That's probably about as many as I know off the top of my head. But I know that I can multiply 9 by a 3 to get a perfect cube of 27. So I'm going to make this a 3. And then if I want to be able to take the cube root of x raised to some power, I'm going to have to at least have x to the third or something divisible by 3. So I'm just going to multiply here by another x. That way when I multiply those two radicals in the denominator, I'm going to create a perfect cube of 27 and x cubed. So when I do that to the bottom, I must also multiply by that on the top so that this is really like multiplying just by 1, and so I'm not changing the problem. So when I multiply in the numerator, then I get 12 times the third root of 3x. Now when I simplify the denominator, the cube root of 27 is 3, and the cube root of x cubed is x. And then I can do a little bit of simplifying further here, and my final answer then becomes 4 times the third root of 3x all over x. These are not going to look very pretty, I can promise you that. So if we go down to letter E, and we look, this time we need perfect fifths. Well, I have a prime number underneath that radical, a 2, so that's really 2 to the first. So I'm just going to multiply by the fifth root of 2 to the fourth, so that I end up with 2 to the fifth, which is a perfect fifth. So here I also multiply by the fifth root of 2 to the fourth. So we get 3 times the fifth root of 2 to the fourth over the fifth root of 2 to the fifth. Notice this is my perfect fifth power. So I can take the fifth root of 2 to the fifth, that's just 2. And I can't take the fifth root of 2 to the fourth, so you can leave that as 2 to the fourth, or you can change it to 16. It doesn't really matter. I'm just going to change it to 16. But if you left it as 2 to the fourth, I would not take off for that. So let's see if you can try F on your own. This is the last problem, the last part of the video. See if you can pause it and do letter F on your own. So this time I'm looking for a perfect fourth. Now I see that I have a 9, and I know that 9 is 3 squared. So I'm thinking if I multiply by 2 more 3's, then I would have a 3 to the fourth power. Okay, so I'm going to change this. multiply by the fourth root of 9, and then to get x to the third to be a perfect fourth, I need another x there. So I'm going to multiply by the fourth root of 9x. So I get 3 times the fourth root of 9x, and then in my denominator I get the fourth root of 81 x to the fourth. So when I simplify, I get 3 times the fourth root of 9x over fourth root of 81 is 3. Fourth root of x to the fourth is x. And then I'm going to simplify here to get a final answer of the fourth root of 9x over x. Give yourself a big pat on the back if you got that one right after you paused the video and then came back and checked it.